let's remember where we were last time. Our plan originally, there's our original plan. Find Centroid, rotate the global coordinate system, AutoCAD mass problem. Then we said, well, it's actually not that simple, because if we look at what the data is, you have to go and you have to change it a bit. So we did some massaging to deal with the fact that it's a list that we get, not just a picture, right? And then at the last session, we were actually sitting here, excuse me, and we got into a whole bunch of mess because we had to remember parallel axis theorem. And there was a problem at the end of last session with the parallel axis theorem. What was it? Does anybody remember?
The distance is not exactly what we were using.
Yeah. We weren't matching what comes out of Rhino, but it's because we didn't accurately translate the parallel axis theorem. So if I go parallel axis theorem, and we look at what the parallel axis theorem says, the R, or the D, is orthogonal to the axis that you want to do, whereas what we were doing was not orthogonal to that axis. So for instance, we said there's a line, right, half his length. I think some of us actually just kind of got half his length, but we said length over 2 is the R, right? So we're actually, when we do IX and IY here, it's completely wrong, because we're not actually doing it orthogonal to what we're talking about here, right? So in other words, if I take a quick screenshot here, this is the kind of, this has nothing to do with computation. This has only to do with engineering or being smart at physics and math. If we want I, Y, Y, right, then and we have a moment of inertia, let's say, about this axis, I, Y, Y star, right? It's not actually that it's, I'm going to exaggerate here, this distance here that we want. That's not right. We want this distance here. And for IXX, the distance would be, obviously, in this situation, it would be from here to here. That's the D. So now we have a new problem. Again, we didn't set out to solve this problem, but in the global scheme of things, we said, spine centroid, global coordinate system, align to, and then get your mass properties going. Now, we've actually said, well, actually, to do all that involves a few other steps, and we've found a few steps along the way. This is just one of those steps. So we've now said, shit, we actually can't just use what we have. This green line on the screen, we've generated it, but we haven't generated the right information. The right information is what I've just sketched in blue. Part of being a computational engineer is just being persistent and being like, okay, I'm getting closer, I'm getting closer. I went from nothing to a line, and now I have to basically come up with what? That's the hypotenuse. I got to come up with, effectively, the two legs. When you're all engineers, it shouldn't be too hard for us to figure out how we're going to go from A to B on paper, right? So, again, now just, again, we're always starting input and output. We can do a very small input-output exercise. We can say, what do I have? And I'll just exaggerate it. I have this. What do I want? I want this and this, where sort of that original one is right here, right? Okay, so let's just, I'll get a blank piece of paper out. And again, this is just another thing we have to do if we want to go past just using engineering software that's out of the box. So, ready? Here we go. Oh, and great, this is perfect. I got the little X, Y. So, input, output, right? So I have this. I want this, and I'll just put a little gap there, this. Ideas. What do we do? And keeping in mind that this is also part of the input here. The input is we also sort of inherit the global coordinate systems, right? So we're already assuming we've been aligned to global coordinate systems. We're not there yet programmatically, but in this example we are. What can we do on paper? Don't worry about the computer. Step one on paper. Who's got an idea? deconstruct it. Deconstruct what? Deconstruct is a Grasshopper term that we learned. Very good job. But we're sitting here right now and we're focusing on just first principles. We don't need Grasshopper for this yet. Again, if you guys should watch the videos if you haven't already. The key thing that we talked about first is if you don't focus on first principles first, you will get lost very easily. Because you won't be able to deconstruct this, for instance, Lily. You won't be able to deconstruct this to do any meaningful, if deconstruct will take the line apart into 2 points. Deconstruct the points will take you to 2 numbers. That's not what we have here, right? So if you were just drawing this on paper and saying, how do we get this out? How do we get these 2 lines out on the left here? 1 and 2. What do we do? And it's not really lines that we want, right? It's more their lengths, but line's a nice, easy way of sort of showing that rather than playing with numbers. Again, why? It's not a trick question, guys. It's pretty easy.
Using both coordinates.
No, I just don't understand. What are you going to do first?
To use. Okay, let's call point A and point B.
Okay, brilliant. I like that.
Then we use the y coordinate of point A and x coordinate of point B to find the.
There you go. So that's one option, right? So what she said is, and again, it comes back to what you know already. So you know that we've gone from this to 2 points. So I'm just going to draw them A and B here. Those are 2 points. And inside of each one of those is x1, y1, z1, x2, y2, z2, right? And you're being clever and you're saying, listen, I can just stitch these back up, these numbers, to get me the points that I want, right? So the first point would be A. On line 1, the first point is A. So line 1 is going to take in a point that is just boom, 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 right? Its second point is a point whose x is different than A, which would come from here, right? Yeah, exactly. And the y would come from here, and the z really isn't unconsequence, but and then it goes in here, and then we would end up with here. Does everybody agree with that? Right? So we're just playing with numbers, right? And that's a brilliant way of thinking. You're actually, I got on you about using the word deconstruct, but actually, the way you're thinking, I just want to make sure that you're staying separate. The way you're thinking is right. Hey, you've given me a line. Inside of a line is points. Inside of a point is numbers. And if I can deconstruct my way down to bedrock, I could probably reconstruct my way back up to something that I want. This is a valid way of doing it, although it's not the way I would do it. So you can do it this way, and that is the right thought process. So there's no right or wrong answer. If it were me, I'd sit there and I'd say, this is just me, I'd say, I can get this, and from there, I can get sines and cosines going on of that theta that can get me over here too. I can also get wacky because I happen to know that there's a few tools at my disposal in Grasshopper that you wouldn't necessarily think of right away. For instance, I would say, well, what if we grab point B and we project him down to the plane? Sorry, I've drawn that. It should be orthogonal, right? If we say project in the y direction, point B or something, he'll end up here. Then it's just connect A to this and this to this, right? There's no right answer. Eventually, when you scale things up, there is a right answer, because if you want to do this 10 million times, there's a more efficient computational way of doing things, because eventually it might take you 10 minutes to run this rather than 1 second. But right now, with the levels you guys are at, it doesn't matter. Lily's algorithm that she's just developed here is correct, and she got there by the right thought process, okay? So I challenge all of you guys right now to try and come up with, you can try Lily's algorithm, but to try and come up with your own algorithm to get down to, given this line that should be on your script, how do I get down to these 2 lines where one is parallel to x and 2 is parallel to y, because at that point you actually have a moment of inertia calculator for any shapes that could go in a pair. So give it a shot. That's the main thing. So we know now. We said before, don't jump to your script yet, but we know we got that line. Geometry is something else we're playing with. Really, the issue is this part of our script, that R, is incorrect, right? So we have to do something with this line that converts that to, if I just sketch it out here, effectively, boom, and then roughly speaking, boom. Okay? Start on paper, and then try and work your way up to something that actually works. If you have the plan on paper, we can figure out how to do it in Grasshopper, for sure. If you don't have that plan on paper, you're never going to get it. Lily, it was your algorithm. Right, let's follow Lily's algorithm. Okay, so what do we do in Grasshopper? We said if we want to find out the word, what's the word if we want to get something inside of something else? So an object like a line has stuff inside of him. So this algorithm here, length, and length over 2 back here, if we go in here, is no good. He's gone. Line comes in, R comes out, and in this case we're looking for IXX, so it's going to be the X direction. So Lily said, let's deconstruct. Uh-oh, deconstruct is not really working for us. Why? Because this is deconstruct a point. So this is obviously part of it, but he's not the end of it. So he's part of it. So I'm just going to move these guys over here. So we said we want to get the endpoints, right? So again, I'm assuming you guys can do the Google search of how do I find the endpoints of a line. Boom, there's the endpoints of a line. And if I just quickly zoom in on that, there's 2 endpoints. Again, if you're doing your practicing, you already know about this guy. And the question is we go back to our roadmap, which tells us what to do. Roadmap here. Point A is going to be interesting because we don't know which one is point A. We've just been given 2 points, a start and an end. We don't know anything about, A and B. So if I'm a smart guy, I go data, I go data's here, and then I go copy this one, and then data's here. Right, so endpoint, start point. So endpoint probably, I've found out heuristically here, endpoint is A in terms of if we map this script to this plan. It looks different because it's going to the second quadrant, right? But it's not that difficult to understand. Now, can I just grab this guy? Will it ever be that the start point is what I want?
Does it really matter?
Depends. How do we know? Remember, it's got to be rule-based, so we have to think now, what will break this? So if I use this guy, let's do it with this guy first, the endpoint. I grab this guy. Well, I got to grab both of them, actually. So this is, let's call him, if I right-click here, B. If I right-click here, A. So let's follow our methodology. So first things first, let's grab a bunch of points, coordinates, and then let's create some coordinates. So construct is the key word there. Construct point, right? We learned about that last time. Construct point, and what did Lily say? We want to take the, for this first point that we want to do, we want to create an X that is equal to which one? Probably B. I want the Y to be equal to the first one, and where do I get it? Oops, what did I do wrong? What's the problem here? My B point is incorrect. Look at where my point ended up. Look at where my inputs were. What, am I using the right point here? No. I should be using the centroid that we've already determined. Because that's really that's how we know. That's the moment of inertia about that point that we want. So I got to bring this guy down here. That's the guy who's A, but now this is the guy who's B. See that? and then ABC. Does that make sense? You see how I'm using green mode to basically tell the story of what's going on here. I'm literally just watching the geometry as we go through the script, and right away I knew before when I did this, it's wrong. The reason I know it's wrong is first principles engineering, not because of scripting. So that's why it's really important to have your first principles down, because now I know that that's right. I know that the distance between this point here and A is for the moment of inertia about the vertical axis, which is y, is the right distance. If I want the moment of inertia about the x, it would have to be which one? I'd have another point I would need, and that point would most likely be B. So it would be the y of B and the x of B. Boom. So the line that connects those two and if I get its length, is 3 units, whatever we're working to. And now that goes up here. We said this is the square root because of the equation. It's doing all the math for us. So now we, in theory, we have determined for the x-axis what its moment of inertia is about its centroid. Right? So if I just take this number, and if I go over here and I say, I think it's mass properties, area moments maybe?
Area moment.
Radius about the moment of inertia about the centroid, 4.186666. IX, 4.48. So it's the same, is it the same order of magnitude? This is e to the 5th. What's this one? About coordinate axes. That's not the right one. About centroid. Oh, sorry, centroid. Here you go. There's a bit of a problem here, obviously, because it says e to the 6th, and we're on e to the 5th. That's a problem right off the bat. Let's see what we did wrong. Okay. Let's just make sure we understand it. IX should be the bigger one. Yes, it is. So we're getting each of these guys' moments of inertia is about their centroids. Here's his area. Is this square root or squared? This is squared. Okay.
This location.
What location? Which one?
Because that's how you have to.
Yeah, I was just about to make this comment. I was leading you guys down a path, and then I kind of forgot it, but we were on that path. Okay, guys, this is the key thing here: is this this idea of which one should we be using in here. I was trying to lead you guys into a trap. The answer was you can't. You can't always just do this, right? Because the key here is remember, this is a list of numbers. So this guy has a centroid that's here. This guy's got a centroid that here, and each of them has its own R. There's the calculation of each one of these guys' little stubs there is going to be different. Does that make sense? Each one of these points needs to be, if I just draw a line off of this horizontal axis here, each one of those points we have to determine its distance from here to here and from here to here. So we need to be thinking about each one of those points themselves, right? So a better approach wouldn't just take in the centroid, take in the centroid, but it wouldn't take in that line and just sort of neglect this point. What we should be doing, in my opinion, is this centroid here. These are the two centroids, right? let's take those in as points, right? Now, I have 2 points here, right? Now, if we want to draw this line for both of them, the key is that we have the starting point for that, both of those lines. You can see it right there, right? 1 line, 2 lines, right? The key now is how do we get down to the points that they connect to? So that one would be, again, I would say, construct a point. You have 2 A's now, right? But we're off. We don't want we want this point right here. Let's see here. So let me just delete all this stuff. Point B here, we don't want to inherit his X value for sure. X value is definitely incorrect. But we do want to inherit his Y value. Did you guys see that? This guy's useless to us. So it was the right thought process, Lily, but it was the sort of, we have to learn how to do it application-wise. So we say, here's our main point. What do we want to grab from him? We want his Y value. Boom. And what do we want from these 2 guys? We want their X values. And these 2 guys, you guys see how the wire is a bit different looking than this one? Because one is 1 item, and the other one is 2 items. Now what we get out the back is 2 points that we can then use with these other 2 points, to draw a line. And you guys see, now I've actually drawn that line parametrically. There you go. There's 2 lengths. And now let's see here. So they're both the same. Let's just kind of fudge it a bit. Again, the way that we're doing the math isn't quite right. So that's going to maybe come to bite us now. So we got the data in terms of the, we can visualize it. That's this centroid's, these 2 centroids distance to the main centroid, let's say the total centroid. And we said Ixx plus A times the square root, the square of this one. If we add those together, let's see here, and then we do a mass addition. Okay, let's see again. I think there's still a problem. .45, and this is to the 5th. So we're off by a factor of 10 if we believe this guy. Did I grab anything inadvertently? Area moments about the centroid.
You moved what profile?
I did it on purpose just to see kind of if we could force something wacky to happen, right? Let's see, let's try and get the moment of inertia about the other. Oh, wait, that's it. Remember last week at the end of the class, we said we weren't really comparing apples to apples. Boom, there it is. Did you guys see that? Okay, the radii, everything we said about this is still correct. Why wasn't it working is because we were saying Ixx plus A times R squared, but we were actually plugging in the Y, right? So we were not playing, again, we were not playing by the same rules that's laid out by the parallel axis theorem. Now if I do it again, and we look, 4.5477, 4.5489. So now, even though we know that our way of finding the centroid is a bit ghetto, you know, for us, this is well within the tolerances of engineering calculations. You're only off by a little bit.
Why do they have some tolerance?
Why does it have some difference? Because the way we're calculating that centroid right now, maybe your centroid remember the centroid of both shapes. We're finding 2 points for the centroid of each shape. We're drawing a line, and we're saying the point between those two lines is the centroid. And I think we determined that's not actually the centroid, which is why if I do area centroid, I actually end up with this one, Bianchi, if you look right there. So we know mathematically our calculation to determine the centroid in this script is not 100% perfect. But in the grand scheme of things, considering the size of this section and everything else, it's probably a pretty damn good estimation, considering we can probably automate it. So we would have to have that conversation. Now, commercially, what do? Do we accept this error and put a contingency on it, or do we fix it and invest more time in fixing this script? But that's a different conversation. So let's go over it one more time. Again, starting on paper, I need to go from this guy right here to 2 guys over here. In the machine, we said what that means is grabbing that centroid point and that we'd calculated, which is a bit incorrect, and the 2 points A and B, that as the B for both points. These 2 points are the centroids of both surface, and with that information, we can actually create a couple other points which actually represent from those centroids the distance to the axis about which we want the moment of inertia. That is the R in the parallel axis theorem. And so long as we're multiplying that by each one of their areas, squaring it, and then adding it to the moment of inertia of both of them about a parallel axis, hence the name parallel axis theorem, which before we weren't. We were doing it against an orthogonal axis, which is not a theorem. There's no such thing as, well, maybe there is, but we're not trying to do orthogonal axis theorem. Then it worked right away. And the way we got there was literally just by using first principles and a little bit of using this green mode to sort of say, I have that point, I have these 2 points, what do I want? I know I want this line, so how can I get it? Well, what if I just construct these points? It's very easy. Green mode's very easy, right? But if you don't have this plan of, I have these, I want this, and therefore to create these is of extreme use to me, because if I have that, then I actually have this. This is what I want. And I don't even really want this. I want this from a checking perspective, right? We don't have to draw a line. We could just do on the canvas here, distance. The distance between this point and this point will be the same as the length, 6.74, that come out. But the reason I'm going to geometry first isn't because I need the geometry. I need the visualization so that I don't spend my time debugging a script that means nothing. We take that number, we put it up here, and we get out the exact same thing that mass props would do. And now for the rest of time, you versus some CADsman, if I move this, I am never going to be beaten by someone who's not doing it this way. Now, obviously, this is maybe, see, it didn't move there because I didn't move it in the right direction. But this will always, always, always beat the guy who's having to sit there, go mass props, write it down, and copy it. We can literally export this number to our calculation package right now. We're ready to go. Now, it's limited. Next time when we come here, we'll have to start talking about now cleaning this up a bit. And I suggest all of you work towards, when you come in here next week, clean this algorithm up so that you have an IX, an IY, and then that would be at the end of this script here. And then at that point, all we have to do is, what do we really only ever have 2 things going in? Right now, this thing, if I put in 3 things, will it work? It won't. It'll break, right? Because it's banking on this hard-coded number of there's item 1 and item 2 here. So we want to make it more generic and therefore more useful. Then we have to do a little bit of work. Equally, we still haven't sorted out the problem of, if I take this guy and I do this, done. If I take this guy and I do this, like, he's obviously not giving us what we want, right? This is doing the math about the x and y. So we'd said, in theory, what we want is to first, if we have this situation, we want to put it back. We haven't done that yet either. This is lesson 4. So let's expedite where we are via moving a bit on our own, and have the idea of next week when we come in here, let's have everybody ready to rock and roll. You should have an IXX and an IYY that completely matches if you do this. Area, moments. Area, moments. If you have that by next week, then we're moving on to getting very close to, this is a tool now you can use on the job. We can't start talking about, the stuff that people want to talk about. How do I feed in all my mullions and have it export to the calcs, and the calcs are done in 1 second? That's not, if that was easy, everybody would be doing it. If that could be done over a lunchtime session, the entire industry would be doing it. It's not that simple. But it's not hard. It just takes some time. Okay? Questions? Sorry for showing up late.